this example is quite similar to the previous example because the definition, a way to define f of g, is the same by considering the case when g is not equal to 0 and or when g is equal to 0. Here, f of g is defined by this. When g is not equal to 0, it is defined by g to the n and g to the e to the g negative 1 divided by g. When g is equal to 0, it is defined by 1, a constant. We can prove this function is entire by using series expansion and also the theorem we have proved. Since Maclaurin series expansion, for this function e to the g negative 1 is this. For every value of g, the representation f of g, which can be constructed by divided by 1 over g, multiplying 1 over g to this both sides. Here is f of g is equal to summation n is equal to 1 to the infinity g to the n negative 1 divided by n factorial, because we multiplied both sides by 1 negative g here and here. This is exactly f of g when g is not equal to 0. On the right hand side, this part will be changed to g to the n negative 1. Okay, so we get this expansion. 1 plus g divided by 2 factorial plus g squared divided by 3 factorial plus g cubed divided by 4 factorial plus, goes like this. Series 5 clearly converges to f of g0 when g is equal to 0. Here, if we insert 0 to the variable g, then we can 1 for the value of f of g when g is equal to 0, which is exactly the same to the definition of f of g. Hence, representation 5 is valid for all g, whether g is equal to 0 or not. And f is therefore an entire function. Okay? F of g is entire function. We just proved. Okay, we can show that, in another way. Since e to the g negative 1 divided by g is equal to f of g when g is not equal to 0. And since f is continuous at g is equal to 0, limit n goes to 0, e to the g negative 1 divided by g is equal to limit n goes to 0, f of g is equal to f of 0, because f is continuous, which is 1. Okay, this is equal to 1. The first limit is evident if we write in the form of like this, which is exactly the definition of the derivative of e to the g negative 1 at g is equal to 0. We observed in section 62 that the Taylor series for a given function f about a point g0 converges to f of g at each point g interior to the circle centered at g0 and passing through the nearest point g1 where f fails to be analytic. Okay, we can enlarge the region but until a point, I mean complex number, here for example g1 where f fails to be analytic. Okay, we can enlarge the circle by this g1. In view of our corollary to theorem 1, we now know that there is no larger circle about g0 such that at each point g interior to it, Taylor series converges to f of g. Because if there were such a circle, f would be analytic at g1. By theorem 1, we have proved. But f is not analytic at g1. So this statement holds. That is, there is no larger circle about g0 such that at each point g interior to the circle, the Taylor series converges to f of g. So a circle comes from the Taylor series. I mean, Taylor series converges. Then there is no larger circle because theorem 1, which says f would be analytic at the region. Okay. Okay, next we have time to meet companion to theorem 1. This prime is kind of friend. That is differentiation